So we have two more topics that we need to deal with in chapter 12 of your text related to particle kinematics. And this one is called absolute dependent motion, which would be pulley systems. So we're going to do a couple problems quickly with pulley systems. And then we'll move on to relative motion analysis. So here we have a pulley system, and the key in dealing with pulley systems is to note that the rope length is constant. All right, and so what we're going to do, so the rope length is constant, and so what we want to do is write an equation related to the length, and then we can take a derivative of that, and then the constant goes away. The derivative of the constant is 0. So if we can have an equation that expresses position relative to the rope, and then take the derivative, we can get velocity and acceleration. All right. So when we go to look at what we need to do is have an equation for each rope. Now, if we look at this problem here, this is going to be the place where I have to do my measurements from. And so notice I have one rope here, real long one, and then I have a second rope. There. So I'm going to wind up having two equations for these ropes. All right. And so I'm given the velocity at A. I want to get the velocity at B. All right. That's logical. So when we do the equations for these things, what we do is we only focus on the part on the rope positions that can change. So what am I getting at? When you go to look at this pulley here, let's look at this big rope. This distance around the pulley never changes. It's a constant. Never changes, so it's boring. This is going to be my datum where I measure from. If I look at the part of the rope from here to there, boring. But however, this distance here and that distance there do change. So those are more interesting to me. Now as I continue along this rope, this doesn't change. Now these are hanging from the ceiling, so this position never changes. And this is bolted to the floor, so this distance never changes. Then the position distance around the pulley is the same, and then this, and then around. So all through here, I don't care. So the only things that can change are as more rope goes into this section, where does it come from? Well, it comes from that section. So I only care about here, here, and there on this thing, if you stop to look at it. So let's just so here what I'm going to do is I'm just going to measure from here to this point right in here. I'm going to call that DC. That's DC by my naming. And then follow this line over. Here we are. And then I'll measure down to this thing. And I'll call that dB. All right. And so here's the thing. So for this rope, the only parts that can change are these three. So I can write the following. 2 DCs, because there's one here and one there, plus dB, equals a constant. Well, if I take the derivative, then I get 2VC, and I'll just bring this plus VB equals 0. Well, I can bring that to the other side if I want. So 2VC equals negative of VB. And that makes sense. So if B is going down, this is going up. If that's going down, B is going to go up. So they'll have opposite signs. All right. Now I got this rope in here. All right. And so I'm going to have the following length. And I'll just put this up here. Call that DA. So I got a rope that goes from here down to there, and then there's that distance. So what's the length of this rope? Well, notice here's DC that takes me from here to this point, and then this one comes on and I go to there. So this rope here is DA minus DC. That's that distance right in here. And then I got a full dA over there. So this was the first rope, say. So the second rope, I have a dA minus DC. That takes care of all of that. Plus another dA equals another constant. Take the derivative. VA minus VC plus another VA equals 0. All right, so now I have 2VA equals VC. So, and I'm given VA is going down at 5 meters per second. Well, if A goes down, C goes down with it. So the signs worked out. So I have 2 times 5 equals 10. So that's VC right now. All right, and then I go up here. So 2 times 10 equals VB. So VB equals minus 20 meters per second. Now notice, so it was measured positive down. So that means it's going up. And this one's all done. We're going to do one more of these. They're all the same. For every rope, you simply set up a coordinate system and then simply take the derivative off of that. So here I have VA, which would have some corresponding, so I'm pulling rope off. So however much rope I pull off, we'll call that dA. Okay, kind of boring. Then here I have a distance off of that. Here's pulley B. That's dB. All right. Now I've got to, we'll just move these to the other side. So I will have a DC, and then down to this one, so I've accounted for all my distances to my pulleys, so let's just look at rope 1. What am I going to call rope 1? I'm going to call this here, down to here, back up. All right. This distance up here, it's not changing. Don't care about it. I only care about how much pulls off here, and then that's going to come off of these two. So for my first rope, dA is the amount it comes down. dA, then I have a dB, don't care, dB, don't care, plus 2 dB equals some constant. All right, which leaves me with VA equals minus 2 VB. All right, all done with that one. Now for this one, we want to get the velocity of D, and we know A is coming off at 2 meters per second. So if A is coming off at 2, we just determined that VB equal, this goes up, this is going up, equals minus 1 meter per second. Okay, no problem. So now let's look at this one. So we've just done rope 1, so that makes this rope 2 in my world. So let's see. This is DC down to here, but that's dB to there. I need this distance. So that's DC minus dB plus another DC. So I have DC minus dB bracket plus another DC is a constant. All right. So take the derivative. I have 2VC equals VB, or VC equals VB on 2. VB is minus 1. Means VC is minus 1/2 meter per second. All right. Now I have one more of these. So this is going to do the same thing we just saw here. So for rope 3, I have a rope, D sub D minus D sub C, that's for this piece, plus another D sub D equals, I'll just call it K, that's my constant. Take the derivative, I have 2VD equals VC, or VD is 1/2 of VC. So they're both have the same sign, so they're both going in the same direction. No problem. So knowing VC is a half, we're left with VD is minus 1/4 meter per second, which is going up. And that's all. All the pulleys, they're just the same. All right, we'll leave this one right there, and I have 2 more problems left to do. This will be basically relative velocity and acceleration analysis. We'll start that in the next video.